Yeah.
Yes, sir.
I discussed about the homogeneous transform and we had taken examples and we had seen that the homogeneous transform can be used for two purposes. It can serve two purposes. The first was that it could be used to translate or to shift positions of points by a given amount, given a given displacement. And secondly, it could also be used to express the position of one frame shifted with respect to the other frame. It could also represent the rotation of one frame with respect to another, and it could also be used to rotate vectors. Okay. In summary, we can just say that the transform that rotates by R and translates by Q is the same as a transform that describes a frame rotated by R and translated by Q relative to the reference frame. So this summary I have extracted from the book by John J. Craig, but it aptly describes all that we have discussed so far. Now we will proceed to the next um, important topic, and that is how do we fix frames on links. It's very important because we have to fix frames on links, and that has to be in a very systematic manner. It cannot be arbitrary. So this is done using a procedure which we call as a convention. It's a Denavit Hartenberg convention. This is named after its, you may say, its finders or its inventors who devised this convention, and it's called the Denavit Hartenberg convention. And this convention is used, uh, this is used to fix frames unambiguously. Now we will place this in proper perspective. See, in our serial robotic manipulators, we have a number of links and they are arranged in a serial configuration. And we would like to fix frames on each of these links. Now, if we are able to fix frames on these links, as these links move, these frames would move with them. And we have already studied the homogeneous transform. If we can relate the frame, one frame with respect to its previous frame through a homogeneous transform, then we will be able to determine all the relations, all the position vectors. We could determine them in any of those frames. So it's essential for us to fix frames on these links. Now, fixing frames can be a matter of choice, how you wish to fix the frames. But if you wish to do it in a very systematic manner, as outlined by Denavit and Hartenberg, then the level of ambiguity reduces to a large extent. Even in the Denavit Hartenberg Convention, uh, which is in existence, in especially as mentioned in the books on robotics, you will see that two different versions of this convention are presented. Both of them are correct, but I would suggest that you stick to one particular convention, one particular form of this convention version. And that is because if you mix these two conventions, you could get extremely confused. So the suggestion is that you stick to one particular convention, one particular version of this convention, and we will follow the version of the convention which is used by John J. Craig in his book on Introduction to Robotics, the Mechanics and Control of Robotics. Now, what is this convention and what does it do? So, this convention essentially uh, it helps us to fix the frames, but the frames have to be fixed in a systematic manner, and it outlines the procedure for it. Now, for any link which is connected to two other links, one before it and one after it, in a serial configured manipulator, robotic manipulator, uh, we have to have two joints, one for the previous link and one for the next link. So we require a two joint axis. So if we consider a link, let's draw a link. I would first start with the axis. Let's say we have one axis of a link here and another axis of the same link at the other end over here. Okay, and I'm just indicating a direction for this axis. Let's say that this corresponds to one particular direction. Let's say that this link is given, if we are to draw its form, we could have it roughly like this. And say that it's connected to the previous link. Here, like this. Okay. And on this side, let's say that we have the other link here. Now, the geometry of this link exactly is not important. What is important will become clear to you shortly. Is the kinematics, kinematic variables. So I'm just taking this. Let's say that this is connected. It's deliberately that I'm showing it as twisted. So we could have links like this. We could just be a little more realistic on this by cutting this part here also. Of course, I can't make it absolutely like a perfect figure, but this is approximately like this. Now, here, let's say that we have a link, and let us say this link is link. We'll give it a number. Let's say that the number of this link is I minus 1. Okay. Now, on this link, I minus 1 means I could take the values 1, 2, 3, 4, and all, and so on. So this could be link 1, it could be link 2, 3, 4, and so on. Now, suppose uh, we have link I minus 1, then this axis we will consider this joint axis. It is it's written as joint axis I minus 1, and usually we designate it as Z I minus 1. Can all of you hear me?
Yes, sir.
Okay.
Yes, sir.
Yes, sir.
In the same way, this is the joint axis I, and this axis is designated as Z. Okay. So the first thing that is done in this convention is to identify the joint axis. Okay. So first thing is identification of the joint axis. Because it's plural, I'll write it as AXES. So you have the joint axis I minus 1 on one side of the link and joint axis I on the other side. That's for link I minus 1. Now, what is this joint axis? It is actually the axis about which the relative motion of these two links takes place. So here on this side, you have the link I minus 2. So link number I minus 2. Okay, it is in touch, it's in contact with link I minus 1 at this joint. And as you can see that the motion, relative motion between these two joints, it appears to be a revolute motion, and it's taking place about this axis. Okay. In the same way, let's say that we have the joint over here. We could have we could extend this slightly. So we could have the other link over here, and okay. So this is the link I, link I, and it is connecting the joint I with joint I plus 1. Now, this discussion also applies not only to revolute joints but also to prismatic joints. Now, if for example, if the relative motion between the links I minus 1 and I, if it is revolute, then there will be relative change of orientation between these two links about the z axis. And if it is a prismatic joint, then there will be a pure translation relative to each other, and this link will move along the z axis with respect to this link. Okay, so it's possible this discussion is applicable for both, for revolute as well as for prismatic joints. So the first thing that you have to do is identify the joint axis. Okay. Now, the whole discussion is based on the how this how these joint axes, how they are um, placed relative to each other. So the first thing is, you can see that the joint axis zi minus 1 is here and zi is here, and they are separated by a distance. So there is a distance between them. And not only that, you can also see that the orientation of these two axes is not, they are not parallel. The orientation is different. So that means there is a twist over here between these two axes. They are skew relative to each other. So how do we specify this? So that is actually expressed in terms of what we call as the link parameters. So now let us try to figure out what are the link parameters. So the link parameters are like this. The first link parameter, it uh, attempts to, or in fact, it specifies clearly what is the relative position of this with respect to this in terms of distance. How far is it located? How far is this axis located with respect to this? So for that, we draw a common perpendicular to these two axes. Okay. So your first thing is you have to draw a common perpendicular. This common perpendicular to zi minus 1 and zi, because we are now interested in determining what is the distance between them. And if these two are skew, if these two axes are skew, then you will have only one common perpendicular possible. So first of all, let us draw this common perpendicular. Let us uh, draw a line which will appear to be perpendicular. Now, it's tough to show it on a two-dimensional um, figure, but I'll just make an attempt. And let's say that we have this axis here. Okay. So I'll also indicate its direction. Now this axis is perpendicular to zi minus 1, and this is how we are going to represent that. is a common perpendicular. So it is perpendicular to Zi minus 1 and it is also perpendicular to Zi. So this is also perpendicular here. Okay. So this is the common perpendicular. Now, if you measure the length, so this axis which you have got, we are going to designate this axis which contains this common perpendicular, we'll write it as x I minus 1. Okay. And this, because zi minus 1 and xi minus 1 have been identified, this becomes the origin of the frame I minus 1. Naturally, you can easily determine the direction of yi minus 1. But because we don't want the figure to be cluttered, we are just leaving it as it is. So uh, we have drawn this common perpendicular, and now this length which you have for the common perpendicular, length of the common perpendicular, that is from here to here. From the axis zi minus 1 to the axis zi. Okay. And this length, we call as the link length. Okay. We will write its notation. Notation wise, it is written as A, and because it pertains to the link I minus 1, we write it as A I minus 1. And it is actually the link length. So A I minus 1 is the link length. Link length of which link? Yes.
Link I minus 1.
Yeah, it's the link length of link I minus 1. So this is AI minus 1 and it is indicating the link length of. Okay. Now, length has been determined. How far is this axis from this axis has been established. But the next important point is what is the orientation of this axis with respect to this axis? Now, that is also done in a very simple way. What we can do is draw a line parallel to Zi. So we'll take this line and we'll draw a line parallel to Zi and we'll place it here at the origin of this. Okay. And yes. So this is parallel It is parallel to Zi. It is placed here on this origin. So naturally, just as Zi was perpendicular to xi minus 1, this will also be perpendicular. Okay. So here we can also shift these two lines here. Okay. So now you can see that we have this common perpendicular to both Zi minus 1 as well as Zi. Okay. This line is parallel to Zi. Okay. So now you proceed, you keep your thumb oriented along xi minus 1. Okay. So keep thumb oriented along xi minus 1. Thumb of which hand?
Right.
The right hand. So keep the thumb of the right hand oriented or pointing towards the positive xi minus 1 axis, and measure the angle. Measure the angle from Zi minus 1 towards Zi, okay, or the line parallel to Zi. So in this case, we will have this angle going from here, okay, it will go like this, and here it will come like this. This is the arc which will be described here, okay. I think I could make it slightly big. Yeah, so we are going in this direction, okay? Going in this direction. Got it? So now you are having an angle, and this angle which you measure is what we call as the link twist. So this angle, so and measure the angle. It corresponds to link twist. It tells you how much is this axis Zi twisted with respect to the axis Zi minus 1. And we designate it as alpha because it's an angle. We'll use alpha, and because it corresponds to the link I minus 1, we write it as alpha I minus 1. Now you see in this little procedure here, two things are well established. One is the distance of this joint axis with respect to this joint axis. Okay, joint axis at one end of the link with respect to joint axis of the previous link, and the relative orientation in terms of an angle which is measured. So it is the link twist. So the link length and the link twist are clearly determined so far in this procedure. Okay. So these two quantities, they are called as the link parameters. They are called the link parameters. And these link parameters are your AI minus 1 and alpha I minus 1. Alpha I minus 1 is this I minus 1. So it is this angle that you have here. Okay. Of course, the sense of the angle and from where it is measured, that is also extremely important. Now let us, now we have finished only half the story. Let's complete it. Now we have two other quantities to be determined, and those quantities are pertaining to the joint. Now let us consider this joint ZI. Here, it is actually joining the link I minus 1 with the link I. Let's say that this link I is connected further to the axis, joint axis ZI plus 1 over here, somewhere here. And let's say that the common perpendicular over there is, it's deliberately that I'm taking it in this manner. Okay, and let's say that slightly, okay. Now this is also going to be perpendicular. This is also going to be perpendicular to so this axis is going to be perpendicular to ZI as well as to XI minus 1. And it is also going to be perpendicular to, so it's already perpendicular, that is shown here. Um, this joint axis, oh, I'm sorry. Yeah, so we need to show the direction of this here. And we'll designate this as X I. Okay. It's connected further over here, and the length that you measure along this from ZI towards ZI plus 1 becomes the link length I. Okay. So you have the link lengths identified. Now we are interested in understanding the joint variables, what we call as the joint variables. So we have two joint variables. Now what are these joint variables? The first joint variable tells us what is the location of the origin of frame I with respect to the frame I minus 1. But this is done by just specifying the distance along the axis zi from xi minus 1 towards xi. So this distance which you have, this length which you have from here to here, okay, this length is specifying the distance along the joint axis zi of the origin of the frame I with respect to the frame I minus 1. And this is designated as D, and because it pertains to the joint I, it's designated as DI. So you have this is what we call as the joint offset. Okay? We write it as joint offset. And it's designated, so it is actually the length measured along Zi from xi minus 1 to xi. So from where xi minus 1 intersects it to where xi intersects it. Okay? This length is called as the joint offset. And this is, in this case, it is di. Okay. We need one more variable which is called as the joint angle. What is the joint angle? Now, um, if you place this axis, an axis which is parallel to xi minus 1, you place it over here, okay, and you turn from xi minus 1 towards xi, you will get the angle. You will have, so we'll measure the what we call as the joint angle, and joint angle pertaining to the joint I. So you focus on the axis zi. You can draw a line which is parallel to xi here. This is a line which is parallel so this is parallel to xi. Okay, and you are now going to turn from you are going to keep your thumb oriented along zi and turn from xi minus 1 towards xi. Now it would, because this looks on the underside, xi seems to be on the underside, you are just turning from, in fact, I'll also show the lengths here. Yeah. So this angle which you measure, keeping your thumb oriented along ZI and turning from XI minus 1 towards XI. Okay, this angle, because it's on the underside, uh, it looks different. So this one is what we call as the joint angle theta. So it is actually obtained by keeping the thumb oriented along ZI and measuring from XI minus 1 to XI. Okay, and measuring the angle. Okay, so here measuring the angle from XI minus 1 to XI. So this is equal to theta I. Okay. So we have discussed the Denavit Hartenberg convention, and we have got two link parameters and we have got two joint variables. And you can see that we have got a frame, the frame I here with its origin here, and the frame I minus 1 with its origin here. So we started with identification of the z-axis. We determined the x-axis for all the links, and then we specified the orientation of one joint axis with respect to the other joint axis and also the relative position, thus identifying the link length and the link twist. And we also determined the joint offset, that is how far is this origin of this axis located with respect to the previous frame, and also what is the joint variable, that is in terms of the angle, how much is it rotated. So this link with respect to this, what is its uh, joint angle. So that's also discussed. So we have got two joint variables and uh, uh, two joint variables and two link parameters in our discussion today. So I think we will have more detailed discussion on this with examples, and we'll also derive the transformation for the homogeneous transform for transformation between the frame I and the frame I minus 1. So with this discussion, I'm planning to conclude for today. If you have any difficulties so far, please ask me now. Please, if you have any questions, please let me know.
Hello, sir.
Yes.
Sir, how we draw the xi here?
How do we know?
How we draw the xi here?
Yeah, yeah. See, just the same procedure as we did for xi minus 1. I did not draw another link here, but I could have drawn another link here. Here you had Zi, here we have Zi plus 1. Okay. And
Okay.
this is common perpendicular. So it is common perpendicular, Xi is common perpendicular to Zi and to Zi plus 1. Okay. I have not shown Zi plus 1 here because then the figure becomes too messy.
Okay, sir.
Is it clear?
Yes, sir.
Yeah, yeah. Any other query?
Sir,
Yes.
we can also find the all parameter according to draw the parallel along the ZI minus one.
I did not understand your question. Can you please be clear?
सर जैसे मैंने जेड आई के पैरेलल ड्रॉ करके सारे जो सॉर्टेड डिस्टेंस परपेंडिकुलर लाइन ड्रॉ करके सारे पैरामीटर डिफाइन किए उसी तरह से क्या मैं जेड आई माइनस वन के पैरेलल ड्रॉ करके ये सारी चीजें डिफाइन कर सकता हूँ.
For example, we can draw a line Zi minus 1 over here.
Yes sir.
It will give us the same result because you see Zi minus 1 is perpendicular to Xi minus 1. Okay.
Yes
And
sir.
here Zi is also perpendicular to Xi minus 1. Okay. You can see over here. So, perpendicular. Got it?
Yes sir.
If you don't have any further questions, I can conclude for today. If you have, please proceed. Please ask me. Okay, in that case, we'll conclude here for today. Thank you very much for being attentive and have a good day.